Okay, so it's recording. Welcome back to lecture 14 and now part 2. Um, so, uh, in the first session of this lecture, I was telling you properties about um, um, Hermitian operators, which are observables in quantum mechanics. So I was essentially showing to you that the very fact that a measurement can have different values in quantum mechanics implies um, the definition of what we call some uncertainty, which is essentially a measurement of how much the outcomes from your experiment will differ from the expectation value of a quantity. And this was then translated to a generalized uncertainty relation that is valid for any Hermitian operator. And what we have seen is that these uncertainties, they are intimately related to the fact that operators typically do not commute. And quantum mechanics is a theory that encodes the physical properties of your system in operators. Okay, so because they don't commute, you, typically you have these non-trivial relations. And then we just saw that if you have two operators that um, give to you well-defined values for measurements when you perform them, namely if the system is in an eigenstate of these observables, then we have seen that they have to commute. And this is what we call compatible observables. Okay, so now I want to change a bit the topic and speak about how we define position and momentum in quantum mechanics. So in classical physics, classical mechanics, um, position and momentum are crucial quantities that we use to describe a system of particles, a rigid body, and so on. So if you want to treat anything like a set of particles, then knowing the position of the particles and the momentum of the particles is, in principle, all what you need to describe the system, together with the dynamical equations. But now in quantum mechanics, we are seeing that observables, namely quantities that you measure, they are represented by operators. So you can expect that position and momentum will also be represented as operators in quantum mechanics. But there is a crucial difference now, which is the following. So in these lectures, I focused on a very particular system, which was the photon polarization. And this is a system that typically your measurements will give two possible outcomes. Okay, so this is a two-level system, but a position of a particle, you can imagine, is not a quantity that will have a discrete set of values. So if I throw a particle in space, I mean, there are infinitely many possible values for the position of this particle. So since the outcomes of a measurement are associated with the eigenvalues of an operator, then unlike the systems we discussed before, the spectrum of the position operator will not be discrete in the sense of having just a finite possible set of values. I mean, in particular, it can have a continuum spectrum. So how do we deal with operators that have a continuum spectrum? This is the main message of this part of the discussion. And I'm going to do this discussion with a view towards position and momentum. Okay. So if you have an operator psi hat with a continuous spectrum, and by continuous spectrum, I mean it will have a set of eigenstates that I call ket psi prime. If you act with the operator psi hat on this ket, then you're going to get a number, which is the eigenvalue associated with this operator and this eigenstate, times the eigenstate itself. But pay attention to the fact that psi prime now is a continuum variable, so it can assume infinitely many values. And this is different from what we are discussing. So for instance, we were discussing about some operators that were 2x2 matrices, which have two eigenvalues. So you can have two possible values. And here I'm talking about eigenvalues that can range from minus infinity to plus infinity, for instance. So we used many facts about Hermitian operators that were facts or theorems based on the fact that these operators had a finite basis or a finite set of eigenstates. But now I'm saying to you that I can have operators with an infinite dimensional basis. So this is a generalization from finite to infinite dimensional vector spaces. Okay, so you as far as I understood, you took a course on functional analysis, and this is, let's say, the arena that makes these things well defined. But here I'm not going to bother too much with the mathematical rigor, and I will just focus on a more intuitive picture. First, because we don't have time, and second, because I'm not a mathematician, so I cannot provide you, let's say, very careful statements about that. Okay, so let's try to understand how to generalize the concepts that we have seen for finite dimensional vector spaces to infinite dimensional vector spaces. So for finite dimensional spaces, we have seen that if you have two eigenstates, let me call A and B, associated with different eigenvalues, then, I mean, the scalar product between these two eigenstates is a Kronecker delta. Namely, it will be 1 if the states are the same, A and A, and it will be 0, namely these eigenstates will be orthogonal if they are different. So this is the scalar product between two eigenstates is just the Kronecker delta. Now let's think how to rephrase this statement in the continuum or in the infinite dimensional case.
Hello.
Yes?
Please, with the other operators we've looked so far before this new operator, those operators that we've looked so far, are they also in a continuum spectrum or they are special case?
So the operators that we have studied up to now?
Yes.
No, they are finite dimensional operators. So they have a discrete set of eigenstates.
Okay, so they are discrete, but the one we are looking now is on a continuum
Yeah,
spectrum.
yeah,
Okay,
exactly. So I'm
okay,
just refreshing your mind with the previous case. So this is when you have a discrete set, and now I will tell you what
okay,
to do when you have a continuum spectrum.
okay, thank you.
You're welcome. So if you have now two eigenstates of an operator with continuum spectrum, then again, you expect that when these eigenstates are different, they must be orthogonal. So this scalar product must be 0. But if they are the same, then you expect that this must be, well, some sort of 1, because this is exactly what distinguishes um, the the scalar product between eigenstates of that are equal and eigenstates that are different. So if you just take the naive continuum limit, you replace the Kronecker delta by the Dirac delta function that you probably have heard about before. Can someone give a feedback in the chat if you saw that before? I'm talking about the Dirac delta function. So I don't see any response in the chat. Oh, so you didn't learn about the Dirac delta function? Okay. Okay. So the Dirac delta function is a function. Well, it's not a function, it's actually a distribution. But it is defined with the following property. I'm going to speak as a physicist now. It is infinity at x equals to 0 and 0 if x is not 0. So this is a function in quotation marks that has this property. We want to know, please, we want to know when do you have, well, I mean, so far, you just saw the case with finite dimensional spaces. So you have seen observables that were represented by matrices of a finite size. But now I'm telling you that there are some observables that they are not observables that you have just a finite set of values, like the position of a particle. And I'm just explaining to you how to translate the technology that you learned for the finite dimensional case to the infinite dimensional case. Okay? But there is not a recipe on, I mean, when do you have finite or infinite dimensional spaces? I mean, this will depend on what is the problem that you're addressing. What is the difference between this Dirac function and the one used in digital communication? Can you be more specific about that? Because the Dirac delta function is something that you use in several different areas. So you probably use that there as well. But I don't know exactly what you are referring to. So the defining property of the delta function is that the integral from minus infinity to infinity of the delta function is 1. Okay? And in particular, if you have if you have a function. So if you compute the integral of a function, f of x times the delta function, this is going to give you f of 0. Okay? This is the defining property. So you see that the delta function, when it is integrated, it gives you a single value of the function. It gives you f of 0. So I hope it will become clear in the future why the scalar product between these eigenstates must be a Dirac delta function. So it is because you always think about integrals when you are talking about a continuum or infinite dimensional space, and therefore these integrals will integrate this delta function against functions, and then you're going to use this property that I mentioned. But for the moment, just see this delta function as the continuum counterpart of the canonical delta. Okay, I think this will be enough for the time being, and then I'm going to say to you some properties about the delta function when we need. Okay, so the other thing that we saw is that if you sum over the outer product between eigenstates, namely if you sum over A for this outer product, you get the identity. This is also true here, but now I don't sum over psi because psi is a continuum variable, so you can take any real value. So instead of summing, I just replace the sum by an integral. So I have to integrate over all possible values of psi, and this will give to me the identity. Okay. So this is the continuum analog of this property. This is the resolution of the identity in the continuum case. We also have seen that given a state, you can insert an identity here and just use the property of the outer product and write this state in the basis of the eigenstates A. And you can do the same with the continuum case, where you insert an identity here, but instead of writing a sum, you write an integral. And now you are expressing this cat in the basis of eigenstates of the operator psi. So you see that it's the same expression, but I'm just replacing A by psi and the sum by an integral. Okay, this is how you. This is let's say the recipe to go from the finite dimension to the infinite dimensional case. We also have seen that given a state, this state must be normalized. So if I take these coefficients of my state, square them, take the absolute value and square them, and sum over all a's, I must get 1, because it must be normalized. The same is true here. So if I have a state beta, and I expand that in the basis of psi, then if I take each coefficient of this psi's, and I take the absolute value and the square, if I sum over all of them, which in the continuum case is just an integral, then I also have to get 1. So this is the normalization condition. Okay, so we also learned that you have a scalar product between alpha 1 and alpha 2. You can insert an identity here in the middle. So this is you just insert the identity AA, and this will transform this scalar product in the product of these two scalar products. And you can do the same with the continuum case. If you have a scalar product between beta 1 and beta 2, you just insert an identity here. And remember, the identity is given by this expression here. So you integrate over all xi's, and now you have two scalar products to deal with. And finally, if A2 is an eigenstate of A, then when you act with A hat on A2, this will give you the eigenvalue, the corresponding eigenvalue, which is, let's say, A2 times the state A2. And then you're going to have the scalar product A1 times A2, and this has the A2 in front because it's the eigenvalue, and this scalar product by this property here is just the delta, the Kronecker delta of A1, A2. So you can do exactly the same thing. So if xi2 is an eigenstate of xi hat, then xi hat acting on xi2 will give me xi2, and then I'll have the product xi1, xi2. And by the first property here, this is just the Dirac delta function. Okay, so this table here just make the correspondence between properties in the finite dimensional case to properties in the infinite dimensional case. Okay, so far I'm just telling you how to generalize some properties from the from the finite dimensional case to the infinite dimensional case. Okay. Now that you have learned this this correspondence here and here, I want to make the definition of the position operator. Okay. So the position operator, it's denoted by x and hat because it's an operator, and the eigenvectors of x are defined as being those cats that I will label as x prime, in such a way that if I act with the position operator on this cat x prime, I get back a number. So this is a number, this is an operator, this is a number. This is the eigenvalue of the position operator with eigenvector x prime. So this is just the definition of the eigenstates of the position operator. And I'm going to postulate that these eigenstates form a complete set. What do I mean by that? I mean that if I integrate the x prime outer product with x prime, then this is the identity. So I'm postulating that this is the case. And I have to integrate over all possible values of x prime. Then I integrate from minus infinity to infinity. So this is what I mean by a complete set. Okay? And so please be aware that, as I said, I'm putting the hat to say that this is an operator. So it is something that typically will not commute with other operators. And this is just a number. This is just the number that labels the position of the particle. So for a given state beta, I can express this beta in the basis of the position eigenstates. In order to do so, I just take beta, I multiply beta by the identity. So beta is the same as the identity times beta. And this identity is just this integral from minus infinity to infinity of the outer product of the position eigenstates. And then just using the properties that define the outer product, I can glue this bra with this cat, and I get this number. So this is a number now, and this is expanded in the basis of the eigenstates of position. So this is the analog, this expression here is the analog of sum over j equals to 1, 2, and then you use the ej alpha ej. So you see this is the analog of this expression. But instead of writing the state in the polarization basis, I'm writing the state in the position basis. Okay? So, and also instead of summing, I have to integrate. Good. So now let me make an important comment, which is the following. So let's assume that I have a super detector that can tell me, so the detector can tell me the precise, exact position of a particle. So this is, if you think about this in practice, this is nonsense. I mean, your detector has a limitation, and you can say that the particle is actually, I mean, between two points. So the particle is located in a small interval of points. Why I'm saying that? Because we don't have a perfect measurement device, okay? And your device has a size. And I mean, just because it has a particular size, it makes impossible for it to have a perfect resolution. And tells you, I mean, that it will not tell you with 100% precision what is the position of the particle. So in practice, ideally, if I have a state beta and I make a measurement about the position with a perfect device, then my state would collapse to the state of position x prime, which corresponds to the eigenstate with eigenvalue x prime, which is the position of the particle. But in practice, this does not happen. In practice, you don't have a perfect device that will tell you with, I mean, arbitrarily precision that what is the position of the particle. So in practice, what happens is that the device will tell you that the particle is located in between x prime minus delta over 2 and up to x prime plus delta over 2. And your detector is, I mean, gets better when this delta is small enough. So if delta is just a tiny number, then you can say, well, approximately the position of the particle is x prime. But you cannot say that it's x prime with 100% of confidence. So instead of collapsing the state of the particle to the state x prime, you collapse the state that previously was written as a sum on the position basis, to a sum, namely an integral, that goes from x prime minus delta over 2 to x prime plus delta over 2. Okay, this is what happens in practice. You collapse your state from this to this. But of course, I mean, if this delta is super small, then I can assume that this scalar product, x double prime beta, does not change too much within this interval. So this will be essentially some sort of constant, okay? And therefore, if I ask you what is the probability of finding the system in the position x prime, you would just take the expansion of your eigenstate, sorry, of your superposition of eigenstates, square it, sorry, take the absolute value, square it, and this will give the probability. So just looking at this expression, the probability would be this quantity here. So you see that I have the coefficient, but I also have this dx, okay? This is what makes the continuum different from the discrete case, because I have to multiply by this dx. So this is a probability amplitude, and when you multiply, so this is a probability density, sorry, and when you multiply by dx, this gives you the probability of finding the particle in this range. This should be small delta. Just a second. This should be delta. Sorry, there is a comment in the chat. But we knew the position of the electron in our double slit experiment. If you mentioned the yeah, I mean, again, that was an ideal thing, right? I mean, you cannot say what is the exact position of a particle. But of course, in an ideal experiment, I can imagine that I have a device that makes this measurement perfectly. But this is not going to happen in practice. That's my point. Okay. Good. So I can now ask the following question. What is the probability of finding the particle somewhere? I mean, if I consider all points of space, and I say, well, what are the chances of finding this particle in any of those points? Well, then you have to sum over all possible probabilities. So this will be the integral from -infinity to infinity. And well, if the particle exists and you are able to measure all points of space, then you're going to find the particle somewhere, right? I mean, the particle will be located in some point. In other words, this integral must be 1, because you know that adding all the probabilities of finding the particle in different positions, this should add up to 1. As, I mean, I can ask you, what is the probability of finding, after a polarizer, what is the probability of finding the photon polarized in some polarization? Well, the probability must be 1. Okay? So this is demanding that this integral is 1, is what ensures the fact that this state beta is normalized. Okay. You have seen that so far I have spoken about dx, but of course, so I'm assuming that the particle is confined to a line. But of course, I mean, we are interested in describing particles in 3 dimensions. And what you can do is just to generalize everything that I said to 3 dimensions. So instead of having a cat associated with the position x, we are going to have a cat associated with the position with 3 coordinates, x, y, and z. And now I denote this cat with x, y, and z information as the vector x. This is just a notation. And it happens that this cat vector x is a simultaneous eigenvector of the operator x hat, the operator y hat, and the operator z hat, with eigenvalues x, y, and z. So since these eigenvectors are simultaneous eigenvectors of different observables, we have learned that they must be compatible, and therefore they have to commute. So the commutator between x hat and y hat, x hat and z hat, and y hat and z hat must be 0. Okay? So this is just a lot of definitions that I posed to you, but the important part is that the position operator is an operator with continuum spectrum, and that different components of your position, x, y, and z, are defined by different operators, which in turn commute. Okay, this is the important part of this session. So there is a question in the chat. The space at which the particle is located keep changing because the particle is moving. So yes, I mean, if you have a particle that is moving, you don't expect that let's say the position of the particle will be fixed. But when the question that you can make is, what is the position of the particle in a given instant of time? So you are going to ask, what is the position of the particle when you make the measurement? So this is the same, for instance, in classical mechanics. You ask what is the position of a particle at some t equals to something. So at t equals to 0, what is the position of the particle? At t equals to t1, what is the position of the particle? It does not make sense to talk about the position of the particle, period, because typically this position will change with time. Okay? And what I'm saying is that if you are good enough to make a perfect measurement that tells you that the position of the particle is x prime, then you collapse the state at x prime. So you're going to essentially collapse your state to x prime, and every time you make a measurement about x, you're going to get x prime again. And this does not happen in practice. Okay. So, likewise, we can define the momentum operator. The momentum operator is an observable that also has a continuum spectrum, because it is associated with the velocity of the particle, and the velocity of the particle can be, I mean, any number. So what happens is that as I just defined the position operator x, y, and z, I can define the momentum operator in the direction x, the momentum operator in the direction y, and the momentum operator in the direction z. And the eigenstate, which is this eigenstate px, py, pz, it will be a simultaneous eigenstates of these operators px, py, and pz, and with eigenvalues px, py, and pz. And again, because p vector is simultaneous eigenstates of these different operators, then they have to commute among themselves. So momentum, different components of the momentum operator will commute. Now comes a very, very important rule in quantum mechanics. So this is very, very important. We have discussed about position operators and about momentum operators. We have seen that different components of the position operator, and now instead of calling x, y, and z, I will call x1, x2, and x3, just to simplify the notation. And instead of saying px, py, and pz, I'll just say p1, p2, and p3. Okay? We have seen that x1 commutes with everyone here, and that p1 commutes with everyone here. But I could ask, does x1 commute with p1, or does x1 commute with p2? These are operators, and therefore they do not necessarily commute. And there are several different ways of finding that out. All of them are, either they involve a long path that we have to pursue. And since we don't have time for that, I prefer just to state what is the result. If you want to understand this better, I can point out references for you. But you can show, or you can, argue that if you take the component I of your position operator and the component J of your momentum operator, and you compute the commutator between these two guys, you get I times H bar, look, H bar, which is a constant that appeared in the first week of this course with Planck, remember? You have I H bar times this Kronecker delta. This means that if you are computing the commutator between x1 and p1, then this delta is just 1. And then you are seeing that x1 and p1 do not commute. Actually, the result is I H bar. So x1 and p1, or x hat and px hat, do not commute. They are not compatible observables. And if you remember the discussion in the beginning of this lecture, this means that the uncertainty of x and the uncertainty of p of x must satisfy the uncertainty relation, namely the product between these two uncertainties must be bigger or equal than a quantity that's non-zero. This is what is often called the Heisenberg uncertainty relation. It tells you that if your uncertainty in position is decreasing, then the uncertainty in momentum must increase, and the other way around. Now, if you take y and py, this also gives to you I H bar. So y and py do not commute, and z and pz do not commute as well. But if you take x and py, these commute, okay? The commutator between x and py gives a delta of 1 and 2, which is 0. So x and py are operators that commute. X and pz are operators that commute. Likewise, y and px, y and pz, and z px and z py. All of these commutators are 0 if the position and the associated momentum component is not the same as in the position. But if you have the coordinate x and the momentum in the same direction of the component of x, you get a non-zero result. So x does not commute with px, y does not commute with py, and z does not commute with pz. And this is a striking result in quantum mechanics. And what is fantastic about that is that you get H bar. H bar, which was introduced by Planck in the first week of this course, it's popping up again in a commutation relation between position and momentum. This was introduced to explain the black body radiation, and this is popping up now in a completely different context. So you see how this constant is fundamental in the description of quantum mechanics. Okay. So what do we have left? I mean, what is open for us now? You see that if you have a general state psi, you can just insert the identity here which is the sum over x, namely the integral of this outer product of psi, and then you can glue this bra with this cat, and this will give x psi times x. Okay? This inner product, which is called between the bra x and the cat psi, is what is typically known as the wave function. Okay? So this inner product is called psi of x. And given two states, alpha and beta, you can write the scalar product. Again, you can insert an identity here, and this will give to you the complex conjugate of the wave function associated with beta, and this will give to you the wave function associated with alpha. So the scalar product between two states in the position representation is just this integral over x of this product between wave functions. So what I'm saying is that everything that we discussed so far in this course was using this abstract notation of state. But you could, from the very beginning of this course, just decide to represent your states in the basis of position. And when you do that, the coefficients that will multiply the eigenstates of the position operator is what we call the wave function. And this is, in general, how people start quantum mechanics lectures. So they start teaching you how to deal with wave functions, okay? And you learn, you have an entire course on how to solve a dynamical equation that we're going to see tomorrow to obtain the form of the wave function. And then you describe the system by the wave function. But it turns out that the wave function description is not the most useful one when you want to talk about quantum field theory. So this more abstract state notation is more useful. And that's why I'm not describing quantum mechanics using the wave function all the time. But I'm saying that if you have learned or if you have heard about quantum mechanics before, it might be that you learned it or you heard about it using the wave function. And this is exactly the wave function that we spoke about in the beginning of the lectures, which is the Schrödinger wave function. So in a quantum mechanics system, you have interference. We cannot forget about that. And remember, you can describe things as waves, and these waves have their own wave functions. And these wave functions are popping up now for us. Okay? So tomorrow, I'm going to comment a bit more about that. I will introduce to you the Schrödinger equation, namely the equation that tells you how a quantum system evolves dynamically. And my final goal is to teach you how to solve the quantum dynamics of a very important system, which is the harmonic oscillator. And since tomorrow we have just 1 hour for our lecture, I'm afraid that I will not be able to do all this in one lecture, but I will go as far as I can tomorrow, and then I will finish the remaining parts in an extra lecture that will be recorded. Okay? So with this, I will close this session, and I thank you for your attention. And remember, tomorrow in the morning, you have a quiz, and 30 minutes before our lecture, I will be online to talk to you about scientific career, how to proceed with a PhD, and a general chat. Okay, so I will stop the recording and see you tomorrow.